Good morning, folks. So lab last night seemed to be going well when I left about 6:15. Did anything untoward happen? It all worked pretty much as advertised. Good. There were two stations that weren't quite cleaned up this morning. Clean them up. One was station 5, had a monitor left there, and station 18. Do you know where the station numbers are? They're on the side of the CPU. We may start keeping track of which ones are cleaned up, but for lab 1 we're not. A couple of students found some interesting bugs, I guess you'd say. I hate to say bug in my own program, but this test program for the mice, it turns out that the default, which I read the documentation, the man pages for open, but I couldn't quite figure this out, that the default for an open is blocking. And if you're going to put the mouse read in an event loop that draws the state machine, the life state machine, and then asks for a mouse input, you better not block or it stops everything. So what you have to do is open this in a non-blocking mode, and of course there's a flag that does that, which you can either put in the open statement, or you can add 2 lines of code which will force the read to be non-blocking. Of course, when you do that, you better not try and read a non-existent string, so you have to make sure that the byte count actually read is greater than 0. So, and the reason I thought the test program was non-blocking was that whoever wrote this, I just took it off of Stack Overflow like everybody else does, that the code does check that the number of bytes is greater than 0. Why would you do that if you had a blocking read? So one way to do it is to use these 2 lines. The other way to include a mouse read would be to just thread it. Put it in its own thread. Threads are separate execution lines of control. I haven't talked about threading yet. There's some examples on the webpage, and I will talk about them. But you could put a human interaction thread separate from the animation thread. You can even run them on separate processors rather easily if you want to. Let's see. I also did a small clarification on the directions for Lab 1 after watching people last night. I put under this section, read the University Program DE1 SOC manual or page. I put 4 subdirections about how to actually program the board. There are 5 connections to the board. People were forgetting one of them quite often. Are there any questions about Lab 1 at this point? Yeah.
This might be more of a specific question to ask in Lab 1, but I was unable to update my package list, so I couldn't get like an updated version of the virus, antivirus or anything like that. I was wondering if that was a common problem or if that was just me.
So you couldn't do an apt-get update?
Yeah, but everything else was working fine. I mean, everything else I tried was working.
So you could do an apt-get and get the SSH stuff and everything?
Yeah, so it was just the old versions.
I don't know what caused that.
Okay.
That's the first time I've seen it was last night. I don't know whether it's something about the But Mohammed, you got it worked fine for you in the lab, right?
APT get update didn't, like, I didn't try installing the complete packages, but like I was able to install like specific packages like OpenSSH and all those things.
Okay, so it may, I don't know what's up with the update.
Okay. Yeah, just with the
We'll try and figure that one out. I don't know what's up with it.
The antivirus is just freaking out on me, like, this is an old version. Like, drop everything.
Unsafe. So luckily, since you're in 10 space, you're relatively protected. Not completely protected, but relatively protected. As far as I can tell, you cannot get to 10 space from any wireless device. I was under the impression that you could if it was in the Cornell domain, but apparently wireless isn't. Anybody know what the rules are on that?
So, as I understand it, you can add any Ethernet port in Philips Hall to the same network and that it can access it. But in general, on the Cornell network, if it's outside of the Philips Ethernet, you can't get access.
Oh, is that right? So it's even specific to the Philips Ethernet.
To the Rhodes routers, which is Philips, Duffields, and Rhodes.
Okay, so that's the limitation.
Yeah.
Wonderful.
It might be just like your office is connected to it.
Now you can of course do point to point. You could take an Ethernet out of the board, plug it directly into your laptop, and that should work, as long as you don't then try and bridge it onto the network.
You might also be able to do something where the board connects to EC Linux, and then you connect through EC Linux back into the board.
Let me know if you get it working. Hey.
If we get our laptops, one of the MAC addresses on that list, we could also plug our laptops into that same switch.
Yes, you could do that.
If we spoof our MAC address.
If you spoof your MAC address, then you could do that. Now, we have a limited number of MAC addresses, but I think we have enough that if you decide to try that, it's not a disaster. I don't know which machines have spoofable MAC addresses and which don't. Depends on where they pull the MAC address from, but I suspect that most modern machines, you can set them. I think they're loaded at boot time, and you can reload them anytime you want. Anything else on Lab 1? Questions on Lab 1? So I want to continue talking more generally about the EBAB Bus Master that you're going to be using for all of the rest of the labs in the course. And so the general description is on the Avalon Busmaster peripheral page. I want to start by looking at the documentation which comes from Altera on this, which is linked at the bottom of that page, Busmaster. And you'll probably recognize this diagram as the one I copied out for the QSYS page in the last lecture. But this module that you're going to put onto QSYS, this EBAB, mediates between the bus signals on the Avalon bus and a slightly simplified interface on the other side that allows you to interface an arbitrary to control arbitrary addresses on the Avalon bus. There is an equivalent bus slave which allows you to pass an address to an external bus of your choice. So let's say you wanted to use somebody else's bus structure, let's say a Wishbone bus. on this, you could make a Avalon to Wishbone bridge using an Avalon external slave adapter. But I don't think most of the time you're going to want to do that in this class, because most of what I'm going to ask you to do with bus slaves is to take output from the HPS and feed it to your bus masters. And if for that, why not just use a parallel I/O port that already exists? You can put as many parallel I/O ports as you want on the bus, so there's no general limitation to that. I wanted to show you one other this diagram. So to get some idea of how the bus works, if your master is going to do a write request, you set up a write address, you set up the write data, then you bring the write control high, and you wait. And in fact, you wait until the ACK comes back, the bus ACK comes back, then you know that the write is complete, and then you can do anything else, anything you want with the bus lines, with the write and with the data and the address. On a read, you set up the read address, you bring the read high, you wait for the ACK. On the ACK, you read the data, and one cycle later, it's gone. So an inquiring mind will ask, what happens if you raise the read and the write simultaneously? Because there's nothing to keep you from doing that. I have no idea. I don't have time to investigate all the edge cases, but it might be something interesting, or smoke might come out. I don't know. Probably it just won't work. It's a simple protocol. Yeah.
If you hold write for longer after the acknowledge goes high, is that just going to start another write immediately? Or do you have to wait? Do you have to lower write, have acknowledge go low, and then you can start a new write a cycle later?
I haven't tried that either. You mean what? So one cycle later, you keep this high.
And back-to-back write.
I probably do a back-to-back write to the same address, which it's like a no-op, except to use it.
Well, if you change the data immediately when the acknowledge goes high, is that okay, or does you have to set write low so that acknowledge will go low? I
think I don't know that it's defined, but let's see if it says. Indicates completed data transfer. Doesn't say. This is the total documentation, 2 pages. So you could try it. Just keep the data constant and sequence the addresses and see if you write a bunch of memory. But again, bandwidth limitations suggest I can't try every possible thing, although sooner or later I'll break it as many ways as possible. The first example I want to show you is using a bus master to control the VGA core, which is what you're using behind the program in Lab 1. And the video core documentation is much more extensive and does describe the layout of pixels, which you could probably deduce from the code, how to do consecutive addressing versus XY coordinate addressing. Consecutive addressing is going to use less memory. XY addressing is a little easier to decode. Something about the pixel space, the RGB color space. 8-bit RGB space uses 3 bits for red, 3 bits for green, and 2 bits for blue. Turns out you don't have as much resolution in your blue channel as you do in your green channel and your red channel. You have 3 color channels in your eye corresponding to 3 different kinds of receptors, and the blue ones aren't very good at intensity, so you don't need as much information there. And then this data sheet goes into an absolute ton of detail on what each of the modules in the interface looks like. Gives you a huge amount of information about them, and it's almost completely opaque. It's just virtually unreadable. Particularly, let's say I was trying to figure out on the character buffer whether you could change the color of a character. And the entire documentation, I mean, there's a nice explanation of how it works here on this block diagram. But these blocks, presumably, the renderer sets the color. That module is not exposed. Oh well, write your own. I've written at least 3, 4 character generators for different platforms. It's not that much work. 2 days. So the main thing to get out of the VGA is that there's going to be a base address and then an offset for each pixel and a separate base address and an offset for each character. And that's what our bus master is going to manipulate, is the offset to the pixel or the character. So now we're going to drop down to the Verilog level and ask, once you've put a bus master onto QSys and you've exposed that interface we talked about last time that has the bus control signals exposed into Verilog, what next? Well, the top level module has a ton of I/O because all the board I/O has to be here. So every signal that's brought out of the FPGA that you have access to is exposed at the top level. There is in Quartus, there's an assignment editor which you can open under the assignment menu. And the assignment editor tells you the physical layout of the physical pins of the FPGA which are mapped to these signals. Don't mess with that. Yeah, that's physical connections of hardware to the FPGA. You mess with that map, you're done. The VGA signals are one example. There's 6 or 8 VGA signals that come out. There's SRAM for the HPS side. There's Ethernet, flash connections, everything. Oh, LEDs. Oh, that's the HPS LED. There's one HPS LED. Then the port declarations, which describe what all the inputs and outputs do. And then finally, after a whole bunch of header, we get down to the actual code where we're going to define various internal signals on the FPGA. And I occasionally like to use the hexadecimal displays to quickly display numbers. So I wrote a hex decoder that takes binary and turns it into 7 segment. That's this hex digit. The next step, of course, is to turn it into decimal. But there's a little header here which drives the hex digits, the first 4 digits, and then the last 2 digits I just drove to all ones. And since this is inverted logic, that means that all of the segments are dark. Then we get down to the gory details here, where we start the bus master definitions. And the very first thing we're going to need is the video base address, because that defines the address of pixel 00. So the video base address is a 32-bit address of hex 800_0000. It turns out that in Verilog, an underscore in the middle of a number is the same as no character at all. So it's a way for you to make more readable stuff, and that character is just compressed away to nothing when it's interpreted by the compiler. So I typically do 16-bit chunks because I can visually parse 4 digits, but not much more than that. And there's a bus byte enable, a bus read, a bus write data, bus ACK, all the stuff we just talked about as inputs to the bus master. If you will remember in C, when we were computing a pixel pointer last time, we took the base address plus the y coordinate shifted by 10 plus the x coordinate. And we're going to do the same thing here. We're going to do a combinatorial assign to form the bus address, which is going to be the video base address plus the extended x coordinate extended to 32 bits. It's a 10-bit number extended to 32 bits, plus the y coordinate shifted 10. If we didn't extend this before we shifted it, it would be gone. And we're going to assign the bus byte enable 1 byte wide, because all of the transfers we're going to do for video are going to be 1 byte colors. So that sets up the state variables. Then we're going to fall into a state machine that executes on every cycle of one of the, how many clocks? 4 clocks. So it's clock 250, 50 megahertz clock. And the push buttons are active low. So if it's not key 0, pressing key 0 means reset, then we're going to reset all of the bus read, the bus write, the x coordinate, the y coordinate, a timer. The timer is just for debugging. Sometimes I like to put timers into state machines to make sure that the system hasn't just stopped. And then we're going to wait. Well, first of all, if the state is 0, then we're ready to write some more pixels. But it turns out that for reasons I have not figured out, state machines running on the FPGA side have to be aware of the video blanking, whereas the C code does not appear to be running on the HPS side. I don't know why this is yet. But you'll get tearing and flickering. You'll get weirdness. You'll get bogus image unless you wait for the video signal to be in what's called blank mode, VGA blank. And that's active low also. VGA blanking occurs when the VGA monitor is not actually drawing a pixel. When it's drawing a pixel, it's not blanked. When it's drawing a pixel, it by God wants memory right now. 25 million times a second. No waiting, no fooling around. So you have to wait to write until the video is not using it. And at least one of you is going to say, but isn't the RAM dual ported? And the answer is yes. So I don't know why this happens. But I'll show you a workaround that makes it faster than this. So if it's true that the state is 0 and the blanking is happening, then two things are going to happen. We're going to set the state to 2. Why 2, not 1? No reason. And we're going to then run a state machine that 1 pixel at a time goes through every pixel on the screen. Now in lab 2, you are not going to do this because it's very slow. Writing 300,000 pixels requires a significant amount of time. For my testing, I just wrote every pixel to make sure I understood how it worked. You are not going to do that. You are going to write 1 pixel at a time, which is going to be the current state of the state variable of this oscillator that we're talking about, the position state variable of the oscillator. But this example steps through, chooses a pixel, chooses a y coordinate, chooses an x coordinate. The code up above, the combinatorial code, then adds those coordinates to make a bus address. And since everything happens at the same time, it doesn't matter what order it's actually in the program. Then we're going to combine coordinates in various ways to make various patterns on the screen. We're going to set the bus write data to some value. We're going to set the bus write to 1. And then we're going to wait for the bus ACK. So if we've just been in state 0, now we're set to state 2, and we don't do this code until the bus ACK goes to 1, which means the write is done. When the write is done, we set the state back to 0, we set bus write back to 0, and on the next cycle, you go back and do the next pixel. Down in the interface module from the QSYS representation is the code that connects the bus master to these external signals that we've just been manipulating up in the Verilog code. So this interface feeds the QSYS generated bus master, which will then drive the bus with the signals that you're generating. Any questions about this? So the minimum state machine is 2 states. Set up the addresses in the data, hit the bus write to 1, wait until the bus write is, but the bus ACK is true, and then go back to state and then write new address. It is not defined how many state clock cycles happens between those states. You don't care. Although for performance you might. Turns out that if you look at the way a VGA video works, for instance, on every line, which is about 25 microseconds, there is a horizontal sync pulse that comes out of the H-sync line, and then there is color information on the color lines that comes out at a rate of 25 megahertz. The video line, though, will have a blank pulse on it for a while, which is longer than the sync. And my code was detecting the H-sync pulse, actually the blanking pulse, to make sure I wasn't overwriting. That causes an artifact because the very next, the pixel 00, or pixel 0 on the horizontal with coordinate x coordinate of 0, happens 1 clock cycle after the end of the H-sync. So let's say that I detect in state 0 of my code that there is no blanking. That we're in blanking, and therefore can write, but the blanking pulse ends on the same clock cycle, then my write will occur while the VGA is trying to access data from memory on the next clock cycle, and you'll get an artifact. So you need to have a more restrictive limit than the horizontal blanking. And what worked was to use VSync ORed with H-sync. The problem with that was that it dropped the performance a factor of 3 from the unsynchronized version. It looked right, but it was slow. So the next step was to say, how much can I cut things down and still have them work? So the final version of the code, which I won't bore you with right now, but is there, uses a set of timing constraints that I got by trial and error, by cutting the system down 1 cycle at a time until it stopped working. It took a while, but you know, binary search is pretty efficient. So I did a more complete bus master for the audio, but it's in the DSP page. The audio loopback configuration is pretty nice. It shows off a lot of stuff. So I'll do that for a couple of minutes here. Again, there's the usual I/O header stuff at the beginning, the I/O definitions, HPS pins until you can't stand it, then the register declarations, and then the audio controller. And the audio controller is more complicated. Maybe I better show you the audio core. The audio system consists of going out to the hardware, has an ADC input and a DAC output corresponding to a 48 kilohertz 16-bit ADC and a 48 kilohertz DAC. And the nature of sound is that it has to be continuous. You are very sensitive to discontinuities in sample rate. And so this system better produce 48 kilohertz samples all the time. The only way to guarantee that is to have a FIFO in each of these channels to buffer the bursty nature of the Avalon switch fabric with the necessity of having an absolutely regular audio sample at the other end. So there's 4 registers. There's a control register that sets up what all the bits mean. There's a FIFO space register that has 4 different FIFO counts in it in each 1 byte field. And there's a left data and right data register. If you read the register, you get the ADC data. If you write the register, you're outputting to the DAC FIFO. So, this, by the way, is going to be lab 3. So, and we're not going to talk about lab 3, I'm just talking about the bus master at this point. So, we have to be able to look at the FIFO, make sure there is space to store a new value. If we're going to output a new value, we have to make sure that the FIFO isn't full. If the FIFO is full, you just wait. If the FIFO has a slot in it, you write into it. For read, you have to make sure that there's data in the FIFO before you read it. And if there's no data, you just wait. So we have to read and write. We have to read the FIFO. We have to read the read FIFO. We have to read the write FIFO. We have to read and write the data if we're going to do a loop back of audio in to audio out, which is the first step for doing any sort of digital signal processing. And the register map is pretty straightforward. It's the usual kind of thing that you see. Offset 0 is the control. It has write enable and read enable and a few other things. The FIFO space has four fields, and they, for some reason, all right, these bits are all expanded out 1 bit at a time. Then these are, so that's 8 bits, that's 8 bits. That is 8 bits, and that is 8 bits. So this is a read, write, this is a read, left, this is write, left, and write, right. Right, right. So now we go back to this mess, this Verilog, and we see that we have 4 addresses. We have an audio base address. FIFO address is 4 higher because it's 32-bit words, and these are byte addresses. There's a data left and a data right. And then the usual byte enable, bus read, bus write data, bus ACK, as before. I wasn't entirely sure I knew what was happening, so I mapped the FIFO space variable to the red LEDs so I could watch it on the LEDs. Now, I can't actually resolve 48 kilohertz, but it was nice at the beginning. You watch the LEDs go, and they all lit up, and then they all smacked back down as the FIFO filled. And after that, you put a scope probe on one of the LEDs, and you can watch the 48 kilohertz signal. There's actually a better way to do that, and that's to use the GPIO, but that was quick and dirty. Then there's an audio right output, left input. The first version I did had a sine table. I was doing direct digital synthesis, and I was using 32-bit audio, but 16-bit DDS, so I had to shift it 16 bits. The later code I wrote switched all the audio over to 16 bits, so the last example on the audio page is 16 bits, and that's where I'll stay for the rest of the semester. Then we do the direct digital synthesis on the positive edge, hooked to a sine table. The sine table is at the end of the code, and it's really boring. It's a ROM that I specified in, goes on and on and on and on and on. It's a ROM I specified in Verilog. Since I specified it as a ROM, it goes into an M10K block, but because it was easier to set up for me to set up in MATLAB and write the ROM in MATLAB, write the Verilog in MATLAB, because MATLAB is an awesome string handling language. No comment? All right, now we go into the actual state machine. Again, we initialize the state machine. And then in state 0, we set up the read for the FIFO. So we set the address to the audio FIFO address, the bus read to 1, bus byte enable to everything, because we're reading all 32 bits. And then we have to go to state 1, which is going to wait for the ACK. In state 1, we wait for the read ACK. When the bus ACK goes to 1, we go to state 2, but we also then copy the bus read data shifted by 24 to FIFO space. Why 24? It was the high byte that happened to be the count for the write. End the bus read, go to state 2, read the first, set up the read for the left channel. I'm sorry, the write for the left channel. So I was being a little bit cautious, so I said that it had to be at least 2 FIFO slots because I wasn't quite sure how it worked. Set the state to 3, set the bus write data to left audio, bus address to left address, bus enable to 32 bits since I was still using 32-bit sound, bus write. And if there was no space, we just go back to state 0. So if the FIFO in fact had no space in it, we just dump back to state 0 and wait another bus cycle. Try again. But if it did succeed, if the FIFO did have space, then we wait for the bus ACK, set the bus write to 0, and then write the write channel. Again, set up the address, data. And at this point now, 6 states later, we've written the 2 channels. Now we have to read the 2 channels. So we have to read the input FIFO. We have to read the input FIFO, wait for it to be done, and it turns out that the input FIFO is in the low 8 bits, so we just AND this with FF to mask off all the high bits. And if there is something in the FIFO, if the FIFO reads back greater than 0, then we read the left channel, wait for the, but if there is nothing in the FIFO, we dump back to the initial condition to state 0. Then we actually do the read on the bus ACK. We copy the bus read data into the audio, set the bus read to 0. Then set up the write, or the write read, read the write address, set the bus enable, check for the bus ACK, read the write data, and then how does anything else in the whole system know that there's no audio, that there's new audio data? Because everything's happening asynchronously. Every clock block is happening when it can happen. So this code sets a data valid ACK as saying that there's new data for a couple of cycles, and then drops out, and it is up to whatever code you have to read that data when it is available. And I think my code up here does that. If audio input ready, then it loads a new DDS sample. So the audio input then acts as the low speed clock for anything else that's using audio input or output. It acts as the synchronization strobe running at 48 kilohertz for any other process that needs it, like a synthesis or a DSP process. Once again, the bus master interface is the same as generated from QSYS, and all of the interesting intellectual property, everything you're going to do for lab 2, 3, and 4 is going to be manipulating the bus master state. In lab 2, you're going to be calculating a differential equation solution and outputting it to VGA. In lab 3, you're going to be calculating a two-dimensional wave equation and outputting it to the audio core. In lab 4, you're going to be calculating Mandelbrot set and outputting it to the VGA core. So this is all about how to interface, the rest of the course is how to interface custom peripherals, custom hardware accelerators onto the bus so that they can be used either by VGA or by FPGA hardware or by the HPS watching the process. So you would probably want to go home and look at this a little bit, particularly look at the bus master page preparatory for doing lab 2, which we'll start talking about pretty soon. Because, yeah, there's a lot of gory detail. Any questions? Any more lingering questions about lab 1? Okay, I'll see a few of you this afternoon. But anybody from last night who wants to come in and sit around and chat or do a little more work, you're welcome.
So I have a hunch that the